In this video we're going to take a look at some of the challenges from the HackTheBox Cyber Santa Capture the Flag competition. It's running for 5 days and we've got 5 challenges each day, so I'm just going to go through the day 1 challenges now. But let's just go and have a quick look at what the competition's about. You can see here, global competition, 5 days, prize pool just over £8,000, solo CTF, Jeopardy style, so just basically challenges, no kind of boxes to hack, and it's designed to be beginner friendly. And it just tells us here basically it's going to be 5 challenges released each day. You can see we've got 5 web, 5 pwn, 5 crypto, 5 forensics and 5 reversing. And on the 14th of December, I believe, there's going to be a live stream, 14th, with walkthroughs and QA on YouTube, so that'll be worth checking out. Some great creators here. But yeah, with that out of the way, let's go over and take a look at the challenges. I'm going to go over these in the order of the number of solves at the moment. So the one with the most solves is the Forensics Challenge Baby APT. Let's take a look at it. The description says, "This is the most wonderful time of the year, but not for Santa's instant response team. Since Santa went digital, everyone can write a letter to him using his brand new website. Apparently, an APT group hacked their way into Santa's servers and destroyed his present list. Could you investigate what happened?" So we've got a PCAP file to download for this one. I've already got it downloaded. Let's have a look at it here. See here, PCAP, we can open this up with Wireshark, or you could do it with T-Shark or something if you wanted, but it's a bit easier to see what's going on in Wireshark. First thing I normally do is go to statistics, and we can have a look at the file properties and the protocol hierarchy. Conversations can be quite good here as well, just to, depending how hard it is to find a flag. In this case, the first thing I'll do is go to protocol hierarchy, just see what sort of data we're dealing with here. And we've got HTTP, which is likely to be of interest to us unless there's some kind of DNS exfiltration or something like that. So I'm just going to select this as a filter. You can also just type HTTP at the top to do this. And we can see some HTTP requests. We'll go into follow this as a HTTP stream. And we can see that there's been a post request, there's register. I don't see anything in here that would represent a flag. Let's go back and do the same again, just going to filter that by HTTP. We also have this post request to bg.php, so let's take a look at that one. When we take a look at this one, we can see that it was actually a command sent. So there's a PHP file, looks like some kind of shell, and you can send a post request to this PHP file with a command specified in the as the parameter, post parameter. In this case, they've tried to cat out the etc password file, and they've actually got it back as well. I still don't see anything there which could represent a flag. I'm going to close that again. We had a few of those post requests, so presumably we've got a different. We've got some different requests that are being sent off, some different commands to that PHP shell. And right enough, if we get to our last command here, we can see that this is encoded at the moment. So we've got some URL encoding, which makes it a little bit harder to read. Let's go to CyberChef. We can throw that in here and say we want to URL decode. Makes it a little bit clearer, and we can see that it was removing an SQLite file, and it was also calling echo with what looks like a base64 encoded string. So I'm going to copy that, I'm going to replace this here and get rid of our URL decode. We'll go to base64 decode, and now we get our flag. We could probably have also, anytime if you don't know what that encoding is, well, you can go and try some different base encoding methods depending on what the character range is here. And also, even from base64, you can change the alphabet here, so sometimes maybe a different alphabet's been used to encode it. But what I was going to say there is, if you really don't know the encoding and you're out of ideas, you can try to throw this magic at CyberChef, and it'll try to do some different decoding methods. You can see that it identified that this was base64 and brought back our flag as well. Next up is the web challenge, which is called Toy Workshop, and the description says, "The work is going well on Santa's toy shop, but we lost contact with the manager in charge. We suspect that evil elves have taken over the workshop. Can you talk to the worker elves and find out?" So for this one, we've actually got a Docker container to launch, which I've started as well, and we can download the source code as well to take a look at it. This does actually come with a build Docker script which we can use to get this working locally. So sometimes if you're working on a CTF, the server can be quite slow, or you might be sharing instances with other people, or you might want to modify some of the source code to try and help debug the challenge if you're not able to solve it. That's the times when this is particularly useful. I'm going to try and launch this, but it might take a while to boot up, so let's see if it's done by the time I take a look at the code. So I'm going to open up the code with Codium. Another thing to mention with the Docker is sometimes if you're doing challenges where you want it to make a callback, you have to remember it's inside a Docker, so it's not necessarily, you can't just, if you were trying to make a callback from a HTTP service, for example, it's not going to call back to your VM, to your local host that you would expect it to. It's going to be restrained to that Docker, so you would need to get into the Docker shell in order to see any of those callbacks, if that makes sense. Maybe it doesn't, but basically in some cases I think it's easier just to, if you know how to solve the challenge, it's easier just to go straight to the site than it is to get things working in a Docker, particularly when it comes to web challenges, but maybe that's just me. I've opened up the site here anyway. Let's go and take a look at the code. Sometimes there's interesting things in the configurations which can give us a clue as well. I've seen before cases where there was like a log poisoning challenge, and you could tell because of the way the login had been set up in the configuration that that was going to be important. So let's start off here. We've got our, just open up the pages we've got here. So we've got some of our views here. This isn't going to be too important to us. It's the JavaScript that we're going to be interested in. So in our routes here, we can see that we can make a post request to API submit. We can make a get request, obviously that's just going to render the page. We can make a post request and supply a query as the body, and it's going to call this bot reads queries DB. You can see here DB add query. It's going to try and add it, and it's sending that over to them. If we don't send anything, it's telling us basically please fill that in. Alright, so that's one of the options. Another option is we can get queries, but if we do that, it's going to check first to make sure we're calling from the local host. So if we're running this on the remote server, our IP address isn't going to be 127.0.0.1 unless we can find some way to forge that. So sometimes that can be through using headers and things like that, or by, in some cases, forcing the user who is the local host to perform some action for us. So queries is basically going to call result render queries. It's going to grab the queries from the database. So let's go and take a look. Where is this database? We've got a database.js. Alright, so when this is set up, we have ID query created at, okay. Add query is going to insert whatever values are provided, and then get query is going to select all. Okay, that's fine. Let's go. Let me just go back to the. This is our main index.js. Let me go back to see what this bot was about, because we have this bot.js. So we had bot.read queries whenever the post API submit is called. And if we go and have a look at the bot, this is basically a browser which is being set up using Puppeteer. And whenever this is launched, whenever the bot's created, it's going to create a cookie with our flag in it. This is obviously a fake flag for the local testing, but if we're doing it remotely, this will have the actual flag in it. So a bot's created, it has the flag, it's going to visit the local host, we've got set cookie, and then it's going to go to queries. So let's just run over that again. We've got our index.js here. We send this post request, it's going to add the query to the database, which we have here. We can see add query. It's going to insert our query here, and then it's going to, where's it go? And then it's going to call read queries. So it's adding the query and then it's reading the query. And if we go to the read query, this is actually going to, well, we know that, where was the, that's too many files for me to keep track of. It's going to select all from queries, and then it's going to resolve that. So it's actually going to load whatever we insert there. So if we were to insert some HTML or some JavaScript or something like that, it's going to insert it into the database, and then it's going to try and load that as a page. So let's try and steal the flag from the cookies. let's go over to our workshop. We can basically click on one of these elves to get this message up, and we can send something. Let me just send that test as an example. Send off, it's delivered successfully. We can go and have a look at Burp Suite and see the post requests. We can see, yep, this was sent off. We can send that to a repeater and start playing around with it. What I'm going to do is just go ahead here and insert a script. So let's do script. Let's close that off as well. And in here, what we can do is, well, there's a lot of different things we could do. We could have it like load as an image from our server and have like an on error alert or something like that whenever it doesn't find the image, and it'll send us a cookie. What I normally do is just set this to document.location equals, and then we're going to give it a location to visit, and the location we want it to visit is going to be our server. So I've got an alias here, web up, which I'll show you what the alias is. It's grep web up from bash aliases. So this is just to create a HTTP server on port 80, in case you ever see me running that and wonder why it doesn't work for you on your local system. So that's going to get that running, and now what we want to do is expose this to the internet as well. So we can use something like, we could use request bin. You can see I have request bin here, which you can go and log into, and basically it'll give you a proper server on the, not just a local IP address for it to connect to basically. But what I normally use is ngrok. Just type ngrok here to get some examples up. You can see here we can set ngrok and provide a protocol, provide a port, and just some other options we can provide here as well. And this will expose local network services behind NATs and firewalls to the public internet over a secure tunnel, which is exactly what we want to do. We want them to have access to this. Be careful, because obviously anybody that has this ngrok address will also have access to whatever you have on your web server. In this case, I'm inside this web toy workshop. It doesn't really matter too much, but if you were on your desktop and you've got some other things in there that you don't want people to have access to, something worth bearing in mind. So I'm going to do ngrok http 80 because that's what service I want to expose. It's going to give me a address to provide here, and I'll just show then as an example. If I go to this address now in a browser in Firefox, it's now giving me access to this local directory. You can see in here we saw the request that was made, and here in the HTTP server that I've got running you can also see that. So let's go and provide this then as the URL. So it's saying to execute this JavaScript, which is going to change the document location. It's going to change the address to our server. But we don't just want you to access our server, we also want to get a flag, cookie. So here we can say then, we'll close this off and we'll say plus document.cookie, and hopefully this will be it. Let me take a copy of it in case there's any problems. We send that off, and hopefully this is going to store it in the database. It's then going to query the database and load whatever's in there and execute it, and whenever it executes it, it's going to go to our location and it's going to send its cookie as part of the query. So if we go and take a look at our local HTTP server, it took a little while to come through, but you can see here we've got our flag, which is HackTheBox evil elves are rising up. The next challenge is called Common Mistake. It's a crypto challenge, and the description says elves are trying very hard to communicate in perfect secrecy in order to keep Santa's warehouse. Unfortunately, the lack of knowledge about cryptography leads them to some common mistakes. And we've got one file to download in this case. It's called encrypted.txt, and you can see in here we've got some, it's actually in JSON format. Let me move that to enc.json. Oops, move encrypted to enc.json. Let's open it up in Codium. Hopefully we get a bit better formatting. Oh, that's not what I wanted to see. Let me move that to enc.python.py obviously. Let's try and close that down. Alright, that's slightly better. We've got a bit better format here anyway. Basically we've got a couple of different objects. We've got two objects, each of them have an N, and each of them have an E, and each of them have a CT. So we've got a modulus, we've got the encryption value, and we have our ciphertext for each of them. Despite my handle being CryptoCat, I'm not really a big fan of crypto, so I'm going to skip through a lot of the details here, but if you want to learn about this attack type, there's an article here on common modulus, which is basically the issue that we have here. So if we go and take a look at this here, you can see in a scenario basically where Eve has two different ciphertexts of the same message M that have been encrypted with a different exponent but a common modulus. So in our example here, the flag has been encrypted with the same modulus but two different encryption values, two different exponents. So you can go and have a look into the maths here, something I'm not going to cover at all here, but we've also got a script which you can use. In fact, this might be the script that I used. Yeah, it was. Okay. So this was a script that I used, which you can provide the modulus, we can provide the two exponents, and we can provide the ciphertext. Oh no, sorry. This is the one, so it takes type long. So actually, if we try to use this, it won't work. We get an error, something to do with, I think, recursion, or the long being too long or something. So this didn't work for me. So let me just run through the solution that did work. There's something called the RsaCTFTool, which didn't actually, I wasn't able to solve the challenge with this, but it did. I did use it at the beginning to generate some of the parts that we need. So this tool can be used for a variety of different attacks. You can set it, you can specify the attack that you want to use, or you can let it run through all of them. The problem that I normally have with this is that there never seems to be the right options for the values that I have. So in this example, we do have a common modulus, I believe. Let me search here. Common factor between ciphertext and modulus attack. Common factors across multiple keys. But whenever you go to specify them, it doesn't seem to be an option to provide the multiple modulus and the multiple ciphertext. You know, we have uncipher file or uncipher, but we don't have an option to provide two different ones, as far as I can see. Maybe somebody, if you can let me know in the comments if you use this tool to solve the challenge completely, that would be good. But what I used this for was to create a public key. So we want to create two public keys here. This isn't necessarily required depending on how you solve the challenge. You know, different scripts will take in different formats. The reason that I did this was because the script that I did find to solve this takes in your ciphertext and it takes in your public keys, and we don't have public keys at the moment. We've got the values to create the public keys. It also takes in the messages as base 64 as well, so that's worth bearing in mind. And hopefully then this will get us a flag. Let's download this Python file. In fact, let's go and do what we need to do with the RsaCTFTool first of all. So we'll git clone. To get the full features out of this, you need to have a lot of stuff installed, like Sage Math, which I'm not going to install because it takes ages. But I'll just do pip install requirements for whatever Python modules it needs there. It probably doesn't need these, to be honest, to create the key, or probably doesn't need all of them. But once we've done that, we can create our key. Let me just show first of all, if we just run Python RsaTool, you can see it gives us all the different options and things that we need here, or that we might need. And we want to do the public key, which is going to be Python RsaTool. We can do -- create pub, and then we want to specify our n. I'm not sure if we can provide this in hex, or we might need to -e format, or in hex. Okay, it looks like we can do in hex. So the n is going to be the same for both. It's just the e that's going to be different. Where's the e? Okay, this one. We've created our first public key. So I'm going to do sublime key1.pub. I just accidentally copied a blank space and pasted it. Alright, there we go. And then we want to do the same thing. We want to, I'll just type it out again, it's going to take too long deleting that. Python RsaTool -- public, create pub -n. Oh, it's not going to take long because the n's the same. What am I talking about? Alright, so we'll just go back and grab that command, and it's 0x23 for this one. We create our public key, and that's key2.pub. Save that. Okay, so now we want to grab the other script as well. Just going to go and take a copy of that here. wget, and we need to make sure our ciphertext is base64 encoded as well. So at the moment it's in hex format. I'm going to go and take this, we'll say from hex, so making it raw, but now we want to say to base64, and that's our first ciphertext. I'm going to save that as C1. Save that. Oh, sorry. I'm going to change that to C1.b64. Probably doesn't really matter, but I noticed that was the format that they were using in the script. And we need to do the same for our second ciphertext. So we'll do C2.b64. Paste that in, and now we should be able to run this new script. Let me get rid of CyberChef in the background. So we'll do Python, and it's called RsaCM common modulus, and we can pass in, let me see, does it give us the options there? Yeah. So we can pass in our C1 ciphertext, which is going to be C1.base64. Pass in our C2 ciphertext, C2 base64. Our public key 1, so K1 is key 1, and K2 is key 2. Let's try and run it, and we get back our flag. So there's probably quite a few different scripts out there to do this, which take your data in different formats and stuff like that. I also noticed with some scripts that you get some errors around recursion, the depth, or around the length of the numbers and stuff like that. But if anybody solved this with RsaCTFTool alone, I'd be interested to hear how you did it. The next challenge is called Mr. Snowy. It's a Pwn challenge. On the description says, "There's snow everywhere, kids are playing around, everything looks amazing, but this snowman scares me. He's always staring at Santa's house, something must be wrong with him." So we've got a file to download, a binary, so we can get this working locally, and then we'll be able to connect to the server afterwards. Let's go and take a look at it. We've got a flag here as well, a fake flag for testing. Just have a look at that. We can see here we've got a 64-bit LSB executable, which is not stripped, which means we'll be able to see all the original function names and stuff like that. It's still got its symbols in it. We can run something like Checksec to determine what protections are enabled on the binary. So we can see some of that here. It would mention if it had pi, and we can see the stripped and stuff like that. But we can also see here there are no canaries found, so if there was a canary found and we were overflowing the buffer, we would need to make sure that that canary doesn't get overwritten with a new value. So if this did have a canary and we were doing a buffer overflow, we'd basically need to leak the canary and overwrite it with the correct canary. Nothing to worry about because there's no canaries found. We've got full rel row here, so this just means we're not going to be overwriting elements of the global offset table. Again, not too relevant here. And NX is enabled. This is a little bit more relevant, so if we overflow the buffer, we're not going to be able to inject any shellcode onto the stack and expect it to execute. It'll be marked as data only. But that's, again, not too important for this challenge. And finally, pi, as I mentioned, we would have seen that here whenever we check the file type. Pi just basically means that the program will load at different memory addresses each time. But in this case, there is no pi, which means it's a fixed address. The addresses will be the same on the server and on our local host. and we can basically just provide the addresses. We don't need to worry about leaking offsets and things like that. Sorry if that was a bit too much for anybody who's not done any of these Pwn challenges before. None of that's really too important for us, but I just thought I'd cover some of these protections before we get going. So let's make the file executable. Where is it, Mr. Snowy? We'll make it executable. Let's try and run it and just see what happens. We have some animated input. While this looks really cool in the terminal, it's extremely annoying when you're trying to test the binary, because obviously we have to wait for the menus to load up each time. We can say let it be here and it'll just exit the application, which means whenever we run it again we need to wait for all that animation again. The other problem is because it sends these characters with a slight delay between each one. If you're running a script and you're trying to debug it, like PwnTools for example, it will print out a lot of output for each character that it sends, which can make things look a bit messy. Obviously we want to investigate, because let it be just took us out of the menu, and then we can deactivate or we can break it. Let's try and deactivate. It says you do not know the password, mission failed. Alright, so obviously we need to break it if we want to get any further with that menu. So we're just doing a little bit of black box testing here without looking at the code or trying to disassemble or reverse engineer it. We're just playing around to see what these options might do. So what did we try there? We tried to break it, did we? No, we tried to deactivate. Let's try to break it. It says this metal seems unbreakable. The elves seem to have put a spell on it. So both of our options there said mission failed. So let's go and take a look at the code in Ghidra. So we open up Ghidra, we've got our decompiler on the right, we've got our assembly code here, we can access the sections of the binary here, and we've got all of our functions, our imports and our exports and stuff here. We want to jump straight into our main function typically and go and have a look here. We've got set up, most of this stuff is just for the visual stuff that they have set up there. We've got this banner which is going to print out this snowman, and you can see why when it's running through all this stuff that makes debugging a little bit hard, because you have to kind of watch all this happen in the debugger. But we go back, our main functionality is here in the snowman function, and we can see what's this print string. It's going to print out the string which is in the data section of the binary. You can see here on the disassembler what it's printing out, and then we have a buffer up here which is defined of 64 bytes. It's going to read in, so it's actually going to read in only 2 bytes here. It's reading 2 bytes into our buffer of 48 bytes, so there's no buffer overflow there, right? 2 bytes fits inside 64 bytes, so there's no issues. And then we have this atoy. This is like converting a char to a number. So we're providing in a menu number, it's converting it to a integer, and then it's checking to see what the integer equals, and will either investigate or exit, because remember that first time we hit 2 and it just exited. So that's what's happening there. Let's go and have a look at the investigate function. So for the investigate, we've got another buffer which is defined here, 64 bytes of characters. We have it's printing out another message, so that's just printing out our menu option basically to us, and then it's going to read in, but look what it's reading in this time. It's reading in 108, and that's in hex as well, so we can actually go over here and highlight that in the disassembler and see that that equals 264 in decimal. So that means it's reading in 264 characters into this local 48 variable, which is 64 characters. So there's a clear buffer overflow there, right? We can overflow. If we overflow these values, we'll be able to overwrite the return address, so that whenever it returns from this function, it returns to an address of our choice. And that address might be to some shellcode or some ROP gadgets or something that we have aligned set up, but obviously in this case there is no shellcode to execute, so we need to have a look around and see if there's any other functions of interest in here that we might want to jump to. Apart from that, we have what we saw there, so we know that whatever we provide, it exits. We provide 1 and it's going to exit, we provide 2, it's going to exit, so there was no way to get any further through this menu. We had to exploit this buffer overflow. And if we go and take a look at some of the other functions here, I guess we need to try and find out something of interest. We've already looked at investigate, the printing's not going to be interesting, snowman. We can go and flick through these, but we see that we have this one, deactivate camera. And if we right click this and say show references to, it's not actually being called, there's no unconditional calls to this function. And if we go and take a look at it, you can see that basically what it's going to do is going to open a flag.txt. If it's not there, it's going to print out an error, and if it is there, it's going to print out the flag. So right there we've got an address. We could go and grab this address here, 401165, and provide that as the address to overflow the buffer. Or we can go and put together a PwnTools script, and that means we'll just be able to access the actual function names as well. Or we could still use the address, however you prefer. So let's go and verify how many bytes we need to overwrite. If we go back to our snowman function, where we investigate, we can kind of work this out from the stack, but it's also possible to do this in GDB using the cyclic function from PwnTools. So I'm going to open up GDB-PwnDbg and pass in Mr. Snowy. And what I'm going to do is generate a, just to mention here, we can also access all of our functions and stuff in here. We can go and disassemble, deactivate camera, for example, and see that we can get the addresses and stuff here that we might need to do our buffer overflow. We can also access a lot of useful functions in PwnDbg if you just type help and then pick something to get more help on. So you can do like help obscure, and it'll give you more things that you can then run help on. You can also just do tab here and just get a list of other functions that you can call. So there's a lot of stuff you can do in here and a lot of functions you can access from outside. For example, we can get into Radare from here as well. Just do R2, AA to analyze, AFL to list the functions, and then we could go and select one of those and disassemble it with PDF. So if you like using Radare, that's an option in here. But oops, I closed the whole thing down. But yeah, I'm just showing a few things you can do there. In case you can also do PwnDbg, as it says here, PwnDbg filter for a list, and this will tell us a lot of other things that we can do here as well. But what we want to do in this case is run cyclic, and you can see here this generates a very big cyclic pattern. We don't want one that's that big, so I'm going to say cyclic 500, even though that's kind of well over what we need as well. We know it's going to be like 60 or 70 bytes based on the size of the buffer. So we'll generate a cyclic pattern of 500, we'll run the program. We still have to wait for it to do its animations. And we want to investigate. It asks us then, do we want to deactivate, do we want to break it? We don't want to do either. We want to pass in this cyclic pattern and see where the crash happens. So we provide that, and we can see then it's crashed. We have at our instruction pointer here, the address that it would try to access is SAAATAAA. The reason it's not in the RIP, it's on the RSP, is because in 64-bit it won't try to access memory addresses that are illegal, basically. That this can't be a valid memory address, it's not in the correct range, so it won't even put it into the RIP. If you were doing a 32-bit challenge, you would see it go in here. You'd see only 4 characters, because obviously half the address size, and it'd be in the EIP. Now that we know it's SAAATAA, we can just grab some of this and say cyclic-L to look that up, and it'll tell us that the offset is at 72. So if we write 72 bytes and then the address of this deactivate camera function, it should overwrite the return address and send us to that function. So to do that, I'm going to put together a PwnTools script, and I'm going to copy over a template which I always use for all these scripts. So we'll just create this and call it exploit.py, and let's open this up and make the changes we need to. So for anybody who's not seen my Pwn videos before, go back and check them out, because I'm going to cover this in a lot less detail than I have in the past, because I've probably got some repeat viewers who are fed up of hearing it. But this template allows you to easily swap between debugging with GDB, swapping between connecting to the remote server, which we're going to need to do soon, and testing locally. Because we have this GDB option here, we can also set up a script here to set up breakpoints at different locations. We could say we want to break at main or something like that, and we won't then, once that's up and running, we don't have to basically go and make any changes to the code to swap between these three options. I also added this find instruction pointer function in here, which is basically just going to do what we just did in GDB. You can see here we're doing the cyclic pattern and we're calling this function. So let me just show how this works first of all. I'm going to change this to Mr. Snowy. Also here we have the context binary being set, so this is basically going to identify whether this is 64-bit, whether it's Windows or Linux, etc. So that later on it'll know what the context is, and if we don't provide a context, it'll default to the one that the binary is. We've also got debug in here. This is going to look horrible, so I'll show you what happens because of the animations. And apart from that, let's just comment out. Let's get rid of some of this stuff that's not needed. Take that out, and I'm going to comment this out. So all we're doing to begin with is just trying to identify how many bytes we need to write to overwrite the return address. So it's going to launch the program here, and after the send, it's going to send line after the angular bracket, which is what we do see whenever it sends the. Let me go back to. I should just run the program, but you see here the last thing it will send is this angular bracket. So after that we want to send the payload, but actually we don't want to send the payload because we want to first make sure we get into the right menu. So remember, it first asks us, do we want to break it or do we want to do something else? So we want to say after the angular bracket, the first time we want to send a 1, I believe it was 1. The 2 will exit. So it's going to send that. It's going to wait for another angular bracket, and then it's going to send the payload, which is going to be our cyclic pattern of 500 bytes. And then it's going to wait for the program to crash. And then it's going to read the core file, which is dumped, and it's going to grab that stack pointer to find the offset. If you were dealing with 32-bit, you just need to uncomment this line and then comment the 64-bit one. So if we run this now, python exploit.py, you see we get this horrible output because I have it on debug mode and it's sending each character with a slight delay. So we wait for all that to complete, but then we see that it does sends the cyclic pattern, and it reads the core dump, and it finds that the offset was at 72. So this is just this SAAA value that we saw in GDB as well. So everything I did in GDB there in terms of identifying the offset, and the same in here of kind of looking at the size of the stack, you can see the variables here, isn't really needed. You can just use a function in PwnTools to do that for you. And now that we've done that, let's go and finish off the payload. So we're going to start the program, and we're saying here we want to build up a payload, and at this offset, which is going to be 72, we want to send the return address. So we could go and grab that address that I mentioned here. So we could go and put in here 0x4. Where did it start there? Let me go and grab this. So yeah, one way you could do this would be to provide this, and you don't need to worry about the fact that it's 64-bit and we should actually be doing all these zeros, because we've told the program what the architecture is here, so it'll default to 64-bit. Flat is basically going to flatten lists and tuples and strings and numbers and things into using the pack function, so basically using the context we have set there. There's a lot of different ways you can do this syntax wise, so don't worry about it too much. But basically we create that payload, and then we're going to do the same thing again. We're going to say we want to press 1 on the first menu, and on the second menu we want to send our payload. I'm also going to go and turn that debug mode off so we can actually see what's going on. And we run this. We have to wait, obviously, for it to go through the find instruction pointer function. We just don't have all the output now, but that's exactly what it's doing. It found the 72 bytes, and now it's launching the program again. This time it knows where the instruction pointer is going to be. So it sends that off, and we get back our fake flag for testing. Now the awesome thing is, because we have this script set up to swap between local and remote, we can literally just say remote, paste in the server address and the port number, and send this off, and it should come back with our flag. I've been getting this warning a lot, so I see that PwnTools have updated, and you see here they've actually given a link to the bytes section. It's kind of annoying because I just want to kind of disable this message, to be honest, but I think what do we need to change? We need to change something else here to, I think, like encode the payload or something. I don't know. So we've got back our flag here. Nice try, elves, but not good enough. One other thing I forgot to mention there was that we don't have to provide the address here. So because we're loading the binary, we can also say elf.functions or elf.symbols, and then we can also provide this as like this kind of syntax as well. So for us, we wanted the deactivate camera, so I'm going to do deactivate camera, and that should do the same thing for us. In fact, let me also just go here and say prettyprint elf.symbols, so I can just show everything that's there as well. Might as well look at something while it's spending 2 minutes connecting to doing the animations. Okay, we've still got to wait for the offset. I should have just gone and changed that to 72. Okay, so you can see it's printed out all of our symbols here. So we can, whenever we say that we want to access one of these functions, rainbow for example, it's given us the address here as an integer, so it's mapping those. Okay, and you can see we also got back our flag in this one as well. The final challenge is called Infiltration. It's a reversing challenge, and the description says, we got hold of an internal communication tool being used by the elves and managed to hook it up to their server. However, it won't let us see their secrets. Can you take a look inside? So we've got a Docker container for this and a downloadable part. I actually spent a long time on this challenge not realizing there was a Docker container until I saw it mentioned in the Discord and then went and checked. So it caused a great deal of confusion. I really couldn't understand where the flag would be coming from in the code that we have, but let's go and take a look at it. I'm not going to jump straight into the solution. I'm kind of going to go through some of the stuff that I was going through before I realized the Docker container was there and stuff like that. Let's see what we've got. We've got this client. Might be executable already, but let's go ahead and make it executable and try and run a client. It tells us we need a server and a port. Let's do localhost 1337, connection refused. So let's make sure we're listening on 1337. Listen on 137, we run that again, and now we don't get any errors. We go back to our netcat and we can see we've got a connection from our local host on 409.16. Let's try and send something. Say hello. It came out with 2 @ symbols and it reversed the hello that we sent. Nothing happened on the server. Sorry, not on the server. Well, obviously this is it's called client, so client, we're providing the server address and port number to connect to. And we enter in something else. Okay, so it's just come back with the full string now, and it exited the application. We could try it again. We could try and enter in some different values and see what we get. But again, we just see that's being reversed. And yeah, nothing else happens then. We might also want to try and do something like ltrace, which we can use to see what's going on in the background. Oh, we need to make sure we have our server running. And let's try and put in now hello. And okay, so we can see it's doing the send and receive, and it's not really showing us anything else there. Alright, so let's go and take a look at the code. We could have a look at this in GDB or Radare or something. I'm going to go over to Ghidra because we get our decompiled code as well, which is a bit easier to read. Okay, so we'll jump straight into our functions here. This binary is stripped, so whenever we were looking at the Pwn challenge there, let's check the file type again. You see this one actually has got pi enabled and it's stripped, so instead of seeing the main function there and the names of all the functions, it's just been given the offsets as the names. Pi being enabled as well, so let's just do Checksec just out of interest. So all the protections are enabled there. We don't have full railroad, but we have canary found, we have NX enabled and pi enabled, so a sea of reds. Obviously this isn't a binary exploitation challenge, so we would expect those protections to all be there, but just wanted to compare that with the last challenge that we went through. So we go over to our entry function. We can just click the function here that's going to be opened up. You can see just an idea of what's happening. It's asking for the server and the port number. If we don't provide something, we're going to get some errors, socket error, or we're going to get this error here. If we provide everything, our server and a port, and it's able to connect, it's going to call this function as well. We could go through and start renaming these functions. You can use L to rename it, or we can go and start inserting comments around once we kind of work out what they're doing. But there's not too much happening here. We have this ivar1, it's calling a function, and the value that's being returned, if it comes back and it's not 0, it's going to return. If it is 0, it's going to go down to this next function here, which is going to do some other stuff here. We can see untrusted client location, enabling opaque mode. We can see we have our canaries here as well. So remember in the last challenge that was talking about the canaries? Basically this is set up, this local 10 is set up at the beginning of the function, and it's set to a random value basically. And then whenever it gets to the end of the program, it's going to check to see whether this still equals. You can see here it's checking, does it still equal what we assigned it to at the beginning? If it doesn't, then it means somebody has overwritten the value on the stack, and then it's just going to exit the program. So if there was a buffer overflow here, and this is taking in 1032 bytes, but if it was reading in, say 2000, we would need to we'd need to find out what this canary is, and then we need to overwrite the value on the stack with the correct canary to make sure our buffer overflow succeeds. Bit of a detour there, but just in case anybody's new to binary exploitation, it might be of interest. We can flick through the functions here. There's actually quite a lot of functions, so some of them aren't going to be necessary for us. Let me go back to the entry. Let's go back in here, and this is the function that we're going to be interested in because this is what it's going to first. And there's a lot of stuff happening here, but I find it easier to kind of work out what's going on by running this with a script. I actually put together a little PwnTools script to send some input and then return it, and we can set up breakpoints and stuff there. But essentially this is reversing our input. As we saw, whenever we typed hello, it comes back with a reversed input. So it's going to do that. We've got our param1 here. It's going to receive in another value, and then it's going to perform some XORs. You can see it's making sure the length of it is 32. Same here, so it's reading in 32 bytes, it gets another 32 bytes, and it starts doing some XOR operations. And then it's going to send the value back that's been XOR'd. And there's some negation here with this uint conversion. So I didn't realize there was a server to begin with, so I was trying to work out, whenever we send this stuff off, where is the flag actually coming from, because it takes an input from us, and then it takes another input, and then it does some XOR operations, but it's always our input. It's not, we would have to completely guess the flag or know the flag. So obviously I was approaching it wrong. We do have a server to connect to, and the server has the stuff we need. But let me just actually show the PwnTools script that I put together, because it's a little bit different structure in these scripts whenever you have a client and you have a server. So you see in this case we had to do our nc-nlvp, set up a listener on port 1337. So if we're using PwnTools, we also need to do this as well as launching the client. So let me just create a exploit.py. I'm going to copy this over, and this is just the same template that I used in the previous example. You can see I've got some breakpoints set up here, so I was breaking at some different locations in the program to try and see what was going on at the time. The reason I don't just have break and then the full address is because that pi is enabled, so whenever we look at these addresses here, they're actually just offsets, and we won't know what their actual full address is until we run the program. So this is basically just set to run the program, and as soon as the program starts running, it's going to set up these breakpoints for us. Break RVA is going to break at this offset from the pi base. You can get the pi base just by typing pi base in GDB-PwnDbg, and it'll show it. And then we're setting up a listener here on port 1337. We're going to start our program and pass in the local host on 1337, and then we're going to set this client to wait for the connection. So the issue obviously for me here was that I was trying to do this all locally, not realizing we had this remote server. but essentially I sent off some value. We know that it's 32 bytes we need to send off, and then if that's done properly, it'll ask for another 32 bytes. And I was just sending this off to try and work out what was actually happening in the background. Let's run Python exploit. We send that off and we can see, okay, so we've sent this off, it's reversed our first input. We send off another input and it does some XOR operations and we get a value back. If we were to do this with the GDB-PwnDbg, so all I need to do now, because I've got those breakpoints set up, is just type GDB at the end. It opens up GDB in another window. It's set up our breakpoints and it's currently hit a breakpoint. And now we can go and actually have a look at what the instructions are. I can't really remember exactly what breakpoint I set up here. Let's hit continue. You can see here. So you can kind of go through and set up breakpoints on whatever you think might be interesting. In this case, we have a compare. I think this might be around too many windows open. I think this might be around the main function, the entry. So this part here, I believe, 1748. Let's have a look. 1748. No, okay. It's somewhere else. But yeah, I can't remember exactly what these breakpoints were I set up, but just to show how we can do this, we can also then, as we get to places, you know, if, for example, we return from this function, and this doesn't equal, sorry, if this does equal 0, no, if it doesn't equal 0, it's going to return. So if we return from that function and that did equal 0, all we'd need to do is go and set up a breakpoint here where it's going to do that test, or where it's going to do a compare, and then just go and modify that in GDB. So for example, if this RAX is set to 0 and we need it to be set to a 1, we could just do here set RAX equal 0x1. You can see here then that the RAX has been updated, and then we would just hit continue or hit next and let it keep going through what it needs to do. So that's a little demonstration of how this PwnTools script will work with GDB. This didn't help anyway, didn't help me get the flag, because obviously we need to go and do this against a remote server, and if we go and do it against a remote server, the output's a little bit different. Let's go and test it out. Okay, we're going to close this. Let's go and get the server address and port number. We'll do netcat, and it comes back with this output. We can try to enter something in, it just comes back with this same issue. We could actually try and do, even if we do 32 bytes, let me go and grab this. This is 32 here, you can see down here 32 selected, because that's what they need it to be. But if I go and enter this in now as a second input, it doesn't actually take it. And the reason being, whenever this is done, it shows up as like the length as being 1 instead of the length being 32. I noticed that whenever I was debugging it. But if you do this inside of PwnTools, it won't do that. So if we launch a script and connect to this server address and port number, and then send these two off, it will come back with two different values. It does that XOR thing. But it's not the way we want to approach this anyway. We know that the server is going to be loading the flag, which we don't have on our client. So let's go and set up a breakpoint around this function, which is 1753, and we can let's run the program. We're going to run the program with this server address and port number. Actually, I'm going to do GDB-PwnDbg, pass in the client, and okay, now we need to run it with that server and port number. Let me just get that. So we're going to give it this server address and port number. We've just got their untrusted client location. So this didn't happen whenever we ran this locally, right? We didn't get this message. So we can see that it's actually got through to this section of code in here. And this is what's going to be of interest to us. So if we can set a breakpoint up around here, remember this was, let me go back, I'm going to get that function address. 1753. So we can say here break RVA 0x1753. It's not going to let us because the program's currently not being run. So can we break? No, we can't break at main either. Let's do break, maybe it's start I. Okay, that starts at the first instruction, and then we can do our break RVA. We'll hit continue, we hit our breakpoint, and that's the start of this function, which is about to be called, and then I basically just stepped through here, so we can step through next. We can keep going and have a look to see what's in these registers and stuff. Maybe we want to print some of them out and see what's in there. But what I'm interested in is this receive. It's going to call receive again, and we know the send and the receive is sending and receiving stuff from the client to the server. So let's go down to receive, and okay, you can see what's being set up here. This is a socket that's being set up, or buffer. We want to see what's actually retrieved. So next one more time, and we get back our flag. Not quite so opaque. So the flag has been retrieved to the stack, and by setting up a breakpoint there in the application, we were able to retrieve it. We could now go and say x over s RSP. We can print out the flag and just take a copy of it and go and submit that. Another way we could have actually done that is to run the same thing. Instead of netcat, we'll do strace, pass in the binary, server and port number, and we run that, and strace will also retrieve the flag for us. This is kind of like running the ltrace as well, but ltrace doesn't come back with all the information there that we would need. So yeah, we can do that with a debugger, or we can do it with strace. Quite an easy challenge, I guess, considering how long it took me to solve it. I mostly blame the Docker, not knowing about the Docker for that, but I guess it's not the only thing to blame. But anyway, we've got all 5 challenges done. Day 1 complete. Let's just go over again. So in terms of the solves at the moment, we've got 1,500 for baby APT forensics, which was obviously the easiest challenge. Second place was web with 621 at the moment, and then crypto with 427, and then pwn with 325, and reversing with 340. Okay, reversing's actually gone up now. That's good. Yeah, but that'll wrap it up for this video, and hopefully we'll get some more challenges done over the next few days. I'm not sure if I'll be able to get every day done, but let's see. If you have any questions or comments, or you've solved any challenges differently, used any cool tricks you want to let me know about, then just leave a comment below. Thanks.